After making this type of the model, then we will verify the axial forces of the track and also in the deck. And if they are not satisfied, if we need to reduce those axial forces, then we need to try some of the factor with certain changes. So what we can try to change it, what is the factor affecting the axial forces in the track? Firstly, the longitudinal resistance of the track is the major factor, which is the ballast stiffness. So, as you know, the ballast stiffness is different under the thermal load and under the train load. And by changing this as changes of the ballast stiffness, we can see the different axial stress, very large difference will occur. And this above one is for the ballast bed and the other one is for the concrete bed. Since concrete bed has more stiff, so its stiffness is different. And if we compare the results between the ballast bed and concrete bed, about 30% difference we can see. I mean the 30% less in the ballast track, which is the above one. So depending on the condition of our bridge, we can go for the ballast bed or we can go for the concrete bed. And zero longitudinal resistance fastener is the other factor. So if the axial stress is larger than our expectation, then we can review the installation of the GLR, and installing GLR fastener will reduce about the 30% of axial stress. And if we see the factors affecting the axial force in the bridge, not the track this time, for the bridge, firstly the expansion length is largely a factor. As we have compared previously, when it has the 10 different simply span, or the other one has the 5 continuous span. In the case we saw about 2 times axial stress was different. And this 4 type of the deck composition we had a test. First one is the 2 span continuous, and type 2 is 2 different deck with each of them are 2 span continuous, and as you can see the fixed support is at the center. Previous one had fixed support at the beginning, and third one is just a simple support, and fourth one fixed support in the second span. If we compare the result for the type 1, 2, 3, 4, in this case, type 2, it has most smallest axial stress, as you can see from those values. Type 2 was this one. So, since this is the fixed support, so it will have the movement only this length only. Due to this factor, this will have the most smallest axial stress. So depending on the expansion length, we will see quite different results of the axial force. The other factor will be the span length and bending stress, bending stiffness of the deck. So if the bending stiffness will affected by the height of the deck. So if the height of the deck is not enough, we will have the large displacement, and it can exceed the limitation of our displacement limit, which is 8 mm. So we need to have a certain enough height of the deck for that. The other factor will be the support stiffness. And as I showed you, so we can model the pier using the beam element in the wizard, or we can even enter the support stiffness directly using the point spring support. And the support layout is another factor affecting the axial force. So when we have the fixed roller or fixed roller fixed, or roller fixed roller and fixed roller. So with those different conditions, how the axial force will be obtained? Firstly, comparing to those two, the axial force is much less in case of the second support type. And also if we compare those two, we can see the axial stress is much less in case of this case, which has the smaller expansion length. Also, the composition of the span is big factor. So as you can see, if our deck has different lengths, depending on the position of this deck, we can see the different axial stress. After we implement this module, the layer track interaction module, then we had full verification, and we have compared the results with the recommended value of the UIC, which is the International Railway Bridge Standard, and we had the satisfied agreement with this UIC recommended results. So those are the verifications. So that's